received her bachelor's in engineering in electrical and computer engineering from Bangladesh University of Engineering and Technology, and she joined my group in the fall of 2017. And she was my second PhD student. And I'm so glad that she chose to come to my group because many of the uh, things that we achieved together is was led by her, and it was her for her. It was because of her that we got many interesting results. So just to few a little bit more about her. So she started the experimental work on antiferroelectric materials when she started, and she discovered a law called her work led to the discovery of a law called law that we often refer to as Yanovich like law for antiferroelectrics that also describe how the microstructure affects the functional properties of fluoride structure antiferroelectrics. Afterwards, she was also involved in the work we did on antiferroelectric negative capacitance. And so then in the second part of her PhD, she led the development of the ferroelectric field effect transistor process flow in the Georgia Tech. Um, and then she focused on the reliability of ferroelectric field effect transistors. So overall, I believe that she made uh, contributions to the area of ferroelectric technology for memory applications. And she also got a number of awards. She received the Cleaver Award at the School of Electrical and Computer Engineering at Georgia Tech for uh, scoring the highest in the preliminary exam in 2017 or 2018, I believe.
Yeah,
And
18.
right. And then she also won the IEEE Semiconductor Interface Specialist Conference Ed Nicolian Award for the best student paper. And recently, she also received the Cadence Diversity Award. So with that being said, Nujat, so let's get started with your presentation.
Thank you for the nice introduction, Asif. So let me share my screen. Can you see my screen, Professor?
Yes, we can. I mean, I can.
Yeah.
Okay, so hello everyone, I'm Nujhat Tasneem and welcome to my PhD dissertation defense. So the topic of my PhD thesis is ferroelectric field effect transistors for embedded memory applications, an investigation of its key challenges and solutions. So over the past few years, ferroelectric FET have garnered a lot of attention as an embedded memory device. Um, However, there are still a significant number of challenges before we can integrate these ferrofets in the memory space. So in my PhD, I tried to focus on analyzing the device physics of ferrofets in order to have a better understanding on how to address these challenges. So let's get started. Um, so over the past few decades, with the increase of number of processor cores per chip and with the rise of data-intensive computing workload, memory has once again become the critical bottleneck limiting system performance. So the first figure here shows the memory wall problem, which indicates that um, the speed of the memory does not increase as much as the processor speed. Um, so the second figure here shows the von Neumann bottleneck problem, which is the idea that in a typical von Neumann structure, the throughput is limited by the processor being relatively faster than the data transfer from the memory units, which emphasizes the importance of in-memory computing. So in data-centric applications, the game changer could be high-performance embedded memory devices. Unlike standalone memory, these devices share the same silicon as its logic counterpart, enabling efficient data transfer between the processor cores and the memory units. and thus can support in-memory computing architecture. So today we have the embedded SRAM for advanced technology nodes as well as the embedded DRAM, but both of these are volatile memory devices. So in the non-volatile memory space, the workhorse is the eFlash technology. However, this technology has a lot of limitations such as low endurance, slow speed, cost, need for high voltage supply. To fill the gap, several emerging candidates have been investigated in the recent years, each having their own benefits and challenges. The ferroelectric-based memory devices are one of them. So before we get into our main topic, let's talk a little bit about ferroic materials first. So a ferroelectric is an insulator which has a spontaneous polarization that can be switched if a voltage greater than its coercive voltage is applied. Now, when this ferroic material is used in the interfacial layer of a transistor, we get the ferroelectric FET, which has been used as a non-volatile memory device in past years due to its hysteretic nature. Now, how does this ferroelectric FET work as a non-volatile memory? So it's very simple. Any textbook on ferroelectrics will show you this type of curve that shows that when the polarization in ferroelectric is in one direction, you have some value of threshold voltage. However, when the polarization is switched, the threshold voltage also shifts. And the memory window in ferrofets is nothing but the shift in this threshold voltage. So as I've stated before, ferrofets there has been a lot of interest in ferrofets as embedded memory devices due to its CMOS compatibility, scalability, fast speed, low write energy, lower footprint, logic and memory capability, which is very helpful for in-memory computing. However, the most important advantage of FEFET, as we understand, is its low energy performance. So the write energy of an FEFET is comparable to that of an embedded SRAM. So that's why there has been a lot of interest in these devices, as we understand. However, along with the advantages comes challenges as well. So as we understand, there are 4 key challenges in integrating these ferrofets for embedded memory applications. So the first one is the write voltage and memory window problem, which is that even with high enough write voltage, we often do not get a decent memory window out of these devices. The second one is that we want these devices to operate for a minimum number of endurance cycles, which is often a challenge. The third one is that there's a trade-off between speed and memory window in these devices, and we want these devices to operate with a sufficient memory window and with a small enough read after write delay. The fourth one is that we want these devices to be significantly identical to each other and to not vary in time, even after a decent amount of fatigue cycling. So in my PhD, I focused on the first 3 challenges denoted by this red box here. So for embedded applications, for logic compatibility, we need a write voltage which is lower than 1.5 volt. And at the same time, to ensure read margin and immunity to noise and variation, we need a memory window which is at least half a volts. Additionally, we require these devices to operate up to at least 10 to the power 11 endurance cycles with a small enough read after write delay. Now, all these challenges are interrelated, but the reason that none of these have not yet been fully solved is because the device physics of FEFET is still not fully understood, even after multiple studies have been done on them. So in order to address these challenges, in my PhD, I tried to investigate the ferroic materials as well as attempted to do an in-depth analysis on FEFET's device physics. So to that end, I categorized my PhD research into 2 parts. So in my early PhD years, I fabricated ferroic capacitors and investigated their properties, specifically for of zirconium oxide ferroic material. And I also tried to develop a process flow for fabricating ferrofets in Georgia Tech's clean room. And then the next few years, I conducted experiments to investigate the device physics, particularly the trap dynamics in FEFET. So I'm going to go through these topics one by one. So let's first look at my early PhD work. So as I've mentioned before in my earlier works, I used to fabricate MIS and MIM capacitors, which is metal insulator semiconductor and metal insulator metal capacitors, which are very great devices if we want to investigate the properties of the deposited materials. So initially, my studies mostly focused on the less explored ferroic material, zirconium oxide, which shows anti-ferroelectricity. This means that it shows a double hysteretic loop in its charge voltage characteristics instead of the more typical single hysteretic PV loop that can be seen in its more popular counterpart, hafnium zirconium oxide. So some of the earlier reports showed that these zirconium oxide MIM caps can be made non-volatile by using work function engineering. And these devices actually shows a lower switching field and even higher endurance than their more popular counterpart, hafnium zirconium oxide. So this was the initial motivation behind investigating zirconium oxide. So in one of my earlier experiments, I fabricated zirconium oxide MIM caps varying the film thickness from 20 nanometer to 5.4 nanometer and measured their characteristics electrically. So even the 5.4 nanometer zirconium MIM cap shows double hysteretic PV loop, which is a very typical characteristics of antiferroelectricity. So I then extracted the critical fields for all the samples from the switching current versus voltage curves. So then with the help of our collaborator, we were able to extract the critical crystallite size or grain size of all the zirconia samples from their XRD data shown by this figure over here. And the results showed that these crystallite size or grain sizes actually follows a predictive law known as the Jonovic-Dunn law or JKD law, which indicates that the critical switching field in these devices is proportional to the negative 2/3 power of the grain sizes shown by this figure over here. So the results from this experiment hints the possibility of manipulating the operating field or voltage of these samples by controlling the grain size. So this work was published in Advanced Electronic Materials in 2021. So next, we focused our study on MIS capacitor, which is the metal insulator silicon capacitor. So this is basically the gate stack of an FEFET. Now, we saw a very interesting property for zirconium oxide, which is that when this zirconium oxide is deposited on top of a metal in an MFM structure, it becomes antiferroelectric. It shows antiferroelectricity, which is this double hysteretic PV loop. However, when zirconium oxide is deposited on top of silicon in an MFIS structure, it becomes ferroelectric and it shows single hysteretic PV loop. Now, our initial motivation of using work function engineering to lower the switching voltage of these devices cannot really work for MFIS or FEFET structure. Also, zirconium MOSFET shows switching voltage which is too high. So in this case, the switching voltage is around 3.5 to -7 volts, whereas the switching voltage for hafnium zirconium MOSFETs is only ±3 volts. So these results made us shift our attention to hafnium zirconium oxides again, which will be apparent from the later part of my presentation. So at this same time, I was trying to design a process flow to develop ferrofets in Georgia Tech's clean room. So this is the device schematic of our fabricated FET, and this is the process flow for the FEFET. Now, I won't, for lack of time, I won't go through the process flow optimization of ferrofet. However, I want to point out that a majority of my PhD time was spent on this because there was no established CMOS process flow at Georgia Tech at that time. So once this process flow was developed, the first FEFET we made, we used ferroelectric zirconium oxide as the ferroelectric material because at that time we were still working with zirconia. This zirconium oxide was was deposited by ALD by Tokyo Electron. So this is the gates HRTM image of the gate stack of our fabricated FFET, which shows clear interfaces. I also like to point out that the transistor gate length ranges from 1 to 20 micrometer. So the reason we decided to make long channel transistors is because we wanted to understand the FFET device physics due to the ferroelectric physics only, and not because of some other effects like short channel effects. So one of the first experiment we did on these ferrofets was trying to observe the effect of the ferroelectric layer and interfacial layer on the device performance. So I would like to point out that for a conventional ferroelectric material, the switching voltage is only, for example, hafnium zirconium oxide, the switching voltage is only 1.5 volt. But whenever we move on from MIM to MI structure, the switching voltage or the write voltage significantly increases. So the reason is that in an FFET structure, the write voltage depends on the voltage drop across all the layers of the FFET's gate stack, which is the ferroelectric layer, the interfacial layer, as well as the semiconductor channel. So in this particular experiment, we changed the thickness of the interfacial layer and the ferroelectric layer and tried to observe their effect on the device operation. So for this experiment, we fabricated 3 FFETs with 3 different gate stacks. 10 nanometer ferroelectric layer with 2 nanometer IL, 5 nanometer Fe layer with 2 nanometer IL, and 5 nanometer Fe layer with 1 nanometer IL. So we applied the standard memory window characterization technique, which is applying a program pulse and reading the device, and then applying a erase pulse again and reading the device, and extract the memory window from it. And we applied it on all 3 of the devices. So the memory window for a certain program voltage and varying erase voltages for the 3 devices are shown by this figure. So the results of this experiment were summarized using this bar chart, which indicates the variation of the write voltage and the maximum memory window with respect to the ferroelectric layer thickness and the IL layer thickness. So this bar chart indicates that the operating voltage, however we define it, decreases as we decrease the interfacial layer thickness. However, at the same time, the memory window also decreases if the interfacial layer thickness is decreased. So this indicates that there is an inherent trade-off between the maximum memory window and operating voltage with respect to the interfacial layer thickness. So if we want to achieve our target for embedded application, we need to carefully optimize the interfacial layer thickness, keeping in mind that there is a trade-off between the memory window and the write voltage. So these are some key takeaways from my early PhD work, which indicates that grain size follows a predictive law known as the JKD law in zirconium oxide films. We also saw that zirconium oxide becomes ferroelectric in MIS structure and have a higher write voltage than its HZO counterpart, which is why later on we shifted our attention to HZO. We were also able to develop a process flow for fabricating ferrofets in Georgia Tech's clean room. And we also learned that there is an inherent trade-off between memory window and write voltage with respect to interfacial layer thickness. So next, I tried to investigate the FFET's device physics, particularly its trap dynamics. And now I spent the last few years of my PhD in this study, and I will also spend majority of my presentation trying to explain this part of my work. So I further divided this device physics analysis in FFET into 3 parts. The first one is the memory window discrepancy in FFET. Now, what do I mean by memory window discrepancy? So as I've mentioned before, the memory window in an FFET is nothing but the shift in threshold voltage when the polarization is switched. And the maximum memory window that we get out of ferrofets can be theoretically represented by this equation over here, which shows that it is equal to 2 times its critical electric field multiplied by the ferroelectric thickness. But in reality, this is not something we see. So in the next slide, I tried to depict the memory window discrepancy problem in FFET schematically. So if we have an FFET and we try to measure the charge voltage characteristics of the gate capacitor of the FFET by applying a voltage at its gate terminal and grounding the shorted source body and drain, we see a hysteretic PV loop like this. Now, if there was proper electrostatic coupling between all the layers in the FFET's gate stack, then ideally, the memory window that we get from the IDVG curve of the FFET should be equal to the memory window that we get from the PV loop. So for example, if this is the positive coercive voltage and this negative coercive voltage, and this is the program and erase voltage, then in ideal case, the memory window we get from the IV curve should be equal to 2VC. However, as we've mentioned before, this is not something we see experimentally. So if we denote the theoretical memory window as delta VP and the experimental memory window as delta VT, what we end up seeing is that delta VT is much, much smaller than delta VP. And this is the memory window discrepancy in FFET. So to test this, we used a ferroelectric measurement protocol that includes 3 subsequent steps for a given combination of erase and program voltages. So in the first step, we measured the drain voltage, drain current gate voltage curves of an FFET for a certain erase and program voltage combination. So we use the standard memory window characterization technique and extract the experimental memory window delta VT from the IV curve of the FFET. And right after this experiment, we changed the experimental setup using the switch matrix by changing the connection using the switch matrix. So then we apply a positive up, negative down or pumped pulse sequence shown here to the gate terminal, while the shorted source body and drain is grounded. So this 2-pulse scheme in the punt gives us the switched polarization in the ferroelectric layer, denoted by delta PF here, for the same erase program voltage combination. So right after that, we apply a triangular right pulse to the gate terminal using the same connection for the same erase program voltage combination. And from that, we can determine the hysteretic PV loop for the gate capacitor of the FFET shown here. From this PV loop, we can extract the theoretical memory window delta VP. So to summarize, from this 3-step experimental procedure, we can actually extract 4 parameters from the same device for same erase program voltage combination. For the same, first one is the experimental memory window delta VT. Then we get the theoretical memory window delta VP. Then we get the switched ferroelectric polarization charge delta PF. And finally, we get the mobile charge density in the semiconductor channel by multiplying delta VT with the on capacitance. So we did this experiment on 4 different FFETs, a zirconium oxide P-type FFET and 3 HZO N-type FFET fabricated in 3 different facilities. So we extracted the 4 parameters from all 4 of these devices and compared them with one another, shown by these figures over here. So the first figure shows that the experimental memory window delta VT for all 4 of the devices is limited to 1 volt, which is very low. On the other hand, the theoretical memory window delta VP ranges from 2 to 8 volt for all 4 of the devices. Now, this memory window discrepancy arises because of the weak coupling between the ferroelectric charge and the semiconductor channel charge. So the figure here shows that the ferroelectric polarization charge ranges from 1 to 30 microcoulomb per centimeter square, whereas the semiconductor channel charge ranges from only 0.1 to 2.5 microcoulomb per centimeter square. The figures in the next slide also shows the same results. So the second figure here shows that only a fraction of the ferroelectric charge, maximum of 10%, contributes to the semiconductor channel charge, which in turn is responsible for the memory window. And this is why we have very low memory window efficiency, a maximum of 20% in FFETs. So the results from this experiment indicates that only a fraction of the ferroelectric charge is getting electrostatically reflected in the semiconductor channel, while the majority of it, around 60 to 90%, is getting screened at the interface by trap charges. So these results were published in IEEE TED in 2022, And this indicates that trap dynamics plays a significant role in determining FFET's performance. So to that end, we focused in the next experiment, we focused on analyzing the trap dynamics in ferrofets. So in order to do that, we used a technique called split positive up, negative down, or split punt technique, where we applied a series of triangular right pulses to the gate terminal of the FFET and directly measured the switching current through all four of the terminals separately. So we did this experiment on an N-type FFET. So the current flowing through the P-type body terminal should represent the majority carriers or the whole current. On the other hand, the current flowing through the N-type source and drain should represent the minority carrier flow or the electron current. Now, in case of an N-type device, when we apply a negative gate voltage, the device should go into hole accumulation, and there should be whole currents flowing through the body terminal. And then when we apply a positive gate voltage, the device eventually goes into electron inversion. And in this case, we should see electrons flowing through the source and drain. Now, keeping this in mind, let's look at the experimental results of this split punt technique. So first, we applied a negative erase pulse on the N-type FFET. And as expected, the device goes into hole accumulation, and we should see whole current flowing through the body terminal, shown by this blue curve over here. However, what is interesting is that at the same time, we see a significant amount of electron current flowing through the source and drain that can be measured by the split punt technique. Now, what does this mean? This means that initially, when the device is in programmed state and the ferroelectric is pointing towards the right, majority of this polarization gets screened by trapped negative charges at the interface. Now, when we start erasing this program state by applying a negative erase pulse, then this trapped electron starts getting emitted. A portion of this emitted electrons goes to the channel, which has a lot of holes, and gets recombined there. But the main point here is that the amount of emitted electron is so large that even after recombination, a significant portion of it gets collected by source and drain. And this is what we are actually measuring in the split punt technique, and is shown by this red curve over here. So the main point here is that there is an emission of electron when the device is in hole accumulation, and a major portion of it gets collected by source and drain, which we can measure using the split punt technique. A similar effect happens when we apply a positive program pulse. So we should since in this case the device goes into electron inversion, and we should expect only electron currents flowing through source and drain, showed by this red curve over here. But similarly, we also end up seeing an amount of whole emission current flowing through the body terminal, showed by this blue curve over here. So the main point here is that there is emission of electrons when the device is in hole accumulation, and there is emission of holes through body terminal when the device is in electron inversion. So now we wanted to see how these trap dynamics changes with fatigue cycling. So to observe that, we used a standard endurance measurement technique on the FFET and measured its IDVG characteristics for each cycling decade, shown by this figure over here, which shows that as we increase the number of cycling, the memory window eventually keeps on decreasing, which is expected. We also see that the subthreshold swing and the gate leakage also increases, and the peak transconductance decreases as we keep on increasing the number of cycles. So this indicates that there's an overall device degradation happening as we keep on increasing the number of fatigue cycles in these devices. So along with the IDVG characteristics, we also applied the split punt technique on this FFET at each cycling decade. So this is the result of the split punt technique, which we get by integrating the switching currents. So the results from the split punt technique shows that the 2PR value, or the remnant polarization of the FFET's gate capacitor, does not change with cycling. What ends up changing is actually the amount of electron emission, shown by these peaks at the negative voltage side of this figure during hole accumulation, and also the hole emission during electron inversion. So again, bottom line is that 2pr does not change with cycling, but the amount of electron and hole emission are the values which ends up changing with fatigue cycling. So we tried to represent these phenomena quantitatively by these plots over here. So the first plot shows that the memory window starts degrading at around 10 to the power 3 cycles. It becomes almost 0 at around 10 to the power 5 cycle. Interestingly, between 10 to the power 3 and 10 to the power 5 cycle, the 2pr value of the FFET remains almost constant. Again, what ends up changing is the amount of emitted hole and emitted electrons, and both of these values monotonically decreases as we keep on increasing the number of cycling. More specifically, the amount of emitted hole actually becomes 0 at around 10 to the power 5 cycle, which is the same point where the memory window also closes. So this results indicates that it's not the Fe layer, rather the electron and hole dynamics, specifically the hole emission, that plays a significant role in FFET's performance with fatigue cycling. So interestingly, these results are consistent among other different ferroelectric FETs. So we did this same experiment on 3 HZO N-type FFETs fabricated in 3 different facilities, Notre Dame, Georgia Tech, and Rochester Institute of Technology. So the dotted curves here shows the evolution of 2pr with cycling, and the solid curves here indicates the evolution of the memory window with cycling. The first figure here shows that for all 3 devices shows similar degradation mechanism beyond 10 to the power 3 cycles. The second figure here shows that as we keep on increasing the number of cycles, the memory window for all the devices decreases, and it becomes almost 0 at around 10 to the power 5 cycles, which is the same point where the amount of emitted hole also becomes 0. So this indicates that with cycling, additional charges are getting permanently trapped and not getting emitted, which means they're getting trapped into states which has a longer lifetime. So in addition to this, we also tried to see how does this read after write delay changes with fatigue cycling. Now, what is this read after write delay? So this is the delay which is required to recover the memory window in an FFET right after a write pulse is applied on it. So for example, immediately after erase and program pulse, the ferroelectric layer in an FFET is polarized. However, majority of this polarization is screened at the interface by trap charges, and only a negligible portion of it goes into the semiconductor channel, which makes our memory window very low. For example, if the read after write delay was 1 millisecond, we would have got, say, around half a volt of memory window. On the other hand, as time passes, these trap charges starts getting more and more neutralized, and we see more electrons in the semiconductor channel, which increases the memory window as well. So for example, instead of 1 millisecond, if we had waited 1000 seconds, which is approximately 16 minutes, the memory window we read would have increased from half a volt to 1 volt. So the bottom line is that the memory window increases as read after write delay increases. So we try to see how this read after write delay changes with fatigue cycling. So this curve over here shows that up until 100 cycle, the rate at which the memory window increases with the read after write delay is almost constant. On the other hand, after 10 to the power 4 cycles, initially the memory window recovery rate is same as before, but after around 1 second, this recovery rate significantly degrades. So again, this indicates that with cycling, additional less and less traps are being neutralized, which means that additional charges are getting trapped into states which has a longer lifetime, which means they are away from the interface and deeper in the band gap. So the results from this experiment helped us to paint a qualitative picture of trap location and dynamics in FFETs with respect to the energy band diagram. So, for example, initially when the device is in program state, we see the polarization pointing to the right direction. So at this state, the trap states in the acceptor level near the conduction band is completely filled. Now, if we start erasing this state by applying a negative gate voltage, this trapped electron starts getting emitted. So portion of this emitted electron goes to the semiconductor channel and gets recombined with the holes over there. However, a significant portion of these emitted electrons is collected by source and drain. And this is what we end up measuring in the split punt technique. Now, once the eraser is completely done, we now have trap states in the donor level, which are filled. Now, if we wait long enough, which means if the read after write delay is long enough, then this trapped hole starts getting emitted, allowing us to read a larger memory window. Now, our experiment showed that as we keep on cycling the device, the amount of emitted electrons and emitted holes becomes less and less. So which indicates that with fatigue, new traps are being generated that have longer lifetimes, which means they are away from the interface and deeper in the band gap. So this work was presented in IDM in 2021. Now this is just a qualitative model. I want to briefly show you here our work in collaboration with TSMC, where we used the results from our split punt technique and tried to propose a quantitative model for FFETs that reflects the trap dynamics and their role in the device operation. So using this model, we were able to quantitatively extract defect densities, which are essentially discrete and in the order are in the order of 10 to the power 14 per centimeter square, which is pretty large. Also, they are in the vicinity of the silicon oxide interface. And the results from this model also indicated that with cycling, there is a buildup of net fixed charge of predominantly one polarity. And this buildup of net fixed charge is the reason why memory window closes with cycling, even when there is full ferroelectric switching, which is still sustained. So this work was presented in IDM in 2022. So from our work on the trap dynamic analysis in FFET, we saw that rather than the ferroelectric layer, the trap dynamics is the main culprit behind the memory window degradation in FFETs. Also, the degradation of FFETs with cycling is possibly associated with additional traps with longer lifetime or fixed charges. So in our next experiment, we try to do a deeper investigation on the origin of read after write delay in FFETs. So for this, we try to observe the effect of thermal treatment along with fatigue cycling on read after write delay. So the motivation for this work came from an older article, which showed that 400 degrees Celsius forming gas anneal can passivate the interface traps that is created in the initial stress, which is shown by this figure over here. And the second figure shows that the original stress also creates additional bulk neutral traps, which actually leads to the oxide breakdown. And these traps cannot be passivated by 400 degrees Celsius anneal. So the bottom line here is that 400 degrees Celsius forming gas anneal can remove stress-induced interface and oxide traps, but it does not passivate stress-generated neutral traps that leads to breakdown. So again, to reiterate, from this paper, we learned that thermal treatment can heal interface traps responsible for stress-induced leakage, but cannot fully heal neutral bulk traps leading to breakdown. So this is why we try to observe the effect of thermal treatment along with fatigue cycling on read after write delay, because we wanted to understand which traps are responsible for this read after write delay. Is it the interface traps or the bulk neutral traps that are generated at fatigue and responsible for breakdown? So for that, we measured the read after write delay for both P and N-type FFET. Now, in case of an N-type FFET, we see that the memory window is significantly dependent on the read after write delay. So, and if we increase the read delay, the memory window also increases. On the other hand, in case of an P-type FFET, the memory window is completely independent. Of the read after write delay. This means that p-type FFET has immediate read after write capability. So this feature has been shown by earlier in other reports as well. So in this experiment, what we did is that we tried to see how this immediate read after write capability in p-type FFET is affected if we keep on cycling this device. So the results show that in pristine state, the memory window is independent of read after write delay in PFET. And as we keep on cycling the device up until 10 to the power 5 cycle, the memory window is still independent of the read delay. However, after 10 to the power 6 cycle, when the memory window closes, it shows a significant dependence on the read delay, which means that PFET has lost its immediate read after write capability. So this also indicates that with cycling, some sort of traps are being generated that is worsening the immediate read after write capability of p-type FFETs. So to reiterate, when we go from pristine to 10 to the power 6 cycling state, PFET loses its immediate read after write capability. Now, if we do a thermal treatment that includes 400 degrees Celsius, 30-minute forming gas anneal, we see that, interestingly, the memory window of the p-type FFET partially recovers by around 50%. However, the read after write capability of PFET does not recover. And also the slope of the curve or the memory window recovery rate after the thermal treatment shown by this black curve over here remains almost the same as that for an 10 to the power 6 cycled one, which is shown by this red curve over here. So the bottom line here is that thermal treatment does not heal the traps that are responsible for the stress-induced read after write delay in PFETs. So we also evaluated some other parameters and observed their evolution with fatigue cycling. For example, the first figure here shows that memory window decreases with fatigue cycling, which is expected. And this figure shows that the gate leakage and the subthreshold swing increases as we keep on cycling the device, indicating bulk trap generation and interface degradation. Now, interestingly, after thermal treatment, the memory window partially recovers, as shown in the previous slide as well. However, what is interesting is that both the gate leakage and the subthreshold swing fully recovers after this thermal treatment and goes almost to their pristine state. So to summarize, the results show that gate leakage and subthreshold swing keeps on degrading with fatigue cycling, indicating interface degradation. However, after thermal treatment, both these values fully recovers and goes to their pristine state. So this indicates that heating can actually heal the interface traps. However, the older paper also showed that in MOS capacitor, heating cannot heal the neutral bulk trap that is related to the time-dependent dielectric breakdown. And our results from this experiment also shows that heating cannot recover the stress-induced read after write delay in FFETs. So these results strongly suggest that the stress-induced read after write delay in PFET is possibly caused by the bulk neutral traps that is generated during bipolar stress and that leads to breakdown. So these results were published in IEEE TDMR in 2023. So our deeper investigation on read after write delay showed us that this delay in p-type FFET is possibly caused by bulk neutral traps generated during bipolar stress and linked to breakdown. So these are some of the insights that we got from our device physics analysis of FFETs. So we were able to establish a measurement protocol, the 3-step measurement protocol to determine the efficiency in practical FFETs and benchmarking them. We also learned that the memory window discrepancy in FFET is consistent, and rather than the ferroelectric layer, the trap dynamics is the culprit behind it. We saw that the degradation with cycling in FFETs is caused by additional traps with longer lifetime. Also, the read after write delay in PFETs is possibly caused by bulk neutral traps generated during bipolar stress. So next, in the end of my PhD, I also looked at some gate stack engineering approaches to optimally design the FFET so that we can successfully integrate it into embedded applications. However, due to limited time, I was not able to go all the way through with it. and there are still a lot of analysis left to be done in this regard. So as I've mentioned that in my PhD, I focused on the first three challenges of the FFET. Now, using gate stack engineering, it is actually possible to solve all the challenges, but trying to do it simultaneously, it will be very time consuming. So for my experiments, I only focused on the first problem and tried to lower the write voltage. And I also focused on the interfacial oxide layer of the FFET's gate stack. So for my experiment, I used a remote oxygen scavenging technique to lower the interfacial layer thickness in the MFIS gate stack in an MFIS structure. So let's give a brief overview of scavenging technique. So when we use, so in this case, we used a well-known method where a platinum nitride stack is used as the top gate electrode. And titanium is a very reactive material which can scavenge the oxygen from the silicon oxide interfacial layer through the titanium nitride layer. And thus, it can lower the interfacial layer thickness. So for this experiment, we fabricated two ferro MOS caps, one with a non-scavenging top electrode, aluminum titanium nitride, and another with the scavenging top electrode, platinum titanium nitride. Now, with the help of our collaborators in UCSD, we were able to do EDS line traces and acquire the STEM images for both the samples. And the results show that remote scavenging can in fact lower the interfacial layer thickness by almost half. So we also measured the electrical characteristics of these two samples. And we saw that the write voltage of the scavenged sample decreases, which is expected since the interfacial layer thickness is decreasing. However, the decrease in the write voltage is not as significant as we expected. It decreases only by 10%. At the same time, the scavenged sample showed higher 2PR and sharper switching than the conventional non-scavenging sample. So these results were published in ACS AMI in 2022. So bottom line is that the remote oxygen scavenging can lower the IL thickness and also lead to overall device performance improvement. However, the decrease in the write voltage is not as significant in case of silicon-based devices. So an alternative could be we can move to silicon germanium-based substrates, which are more amenable to this scavenging technique. So further study requires to be done in this regard. So to that end, one of our future projects involved shifting our focus to another parameter of the gate stack of the FFET, which is the channel, and we changed it to germanium. So in case of silicon FFET, germanium has a distinct advantage because its dielectric constant is higher and it has a lower band gap, which can actually lower the write voltage. Now, in our silicon FFET, we saw that at 2 volt, there is no switching, and at 3.5 volt, there is around 1 volt of memory window. On the other hand, for our fabricated germanium channel FFET, we saw that even at 1.4 volt, we see half a volt of memory window, which is very similar to our goal for the embedded application. However, germanium FFET shows higher subthreshold swing. Also, we know that germanium channel is prone to more trapping than silicon channels. So there is still a lot of work left to be done in this regard. And in order to properly optimize this germanium channel FFETs, which is currently being done by my group mates, Jing-Sang Park and Deepjyoti Das. So these are some key takeaways from my limited work on gate stack engineering approach and some suggestions for future work. So we learned that remote scavenging can lower the interfacial layer thickness, but cannot lower the write voltage significantly in silicon-based devices. So we can move on to silicon germanium-based channels. Now, changing substrate to germanium has the potential to solve the write voltage and memory window problem. However, there is still long way to go and further study is required in this regard. Finally, the extensive data that was collected in this thesis can be actually aggregated to develop a predictive compact model for FFETs that can reflect the trapping dynamics in these devices. So to summarize my entire thesis, my initial work on zirconium oxide showed that grain size rather than film thickness follows JKD law in zirconia films. Also, we were able to develop a process flow for ferrofets at Georgia Tech's clean room. And we also learned that there is an inherent trade-off between memory window and write voltage with respect to IL thickness. Then through my work on device physics analysis in FFETs, we were able to establish a generalized measurement protocol for benchmarking FFETs. We also learned that the degradation with cycling happens due to additional traps with longer lifetimes. Also, the read after write delay in PFETs is possibly caused by bulk neutral traps generated during bipolar stress. And then my limited work on gate stack engineering revealed that remote scavenging can lower the IL thickness, but cannot lower the write voltage significantly in silicon-based devices. Also, a germanium channel has the potential to solve the write voltage and memory window problem in FFETs. However, much more further study is required in this regard. So this is a list of some of my publications. And with that, I will end my presentation here. Thank you for listening to me patiently.